I'm Jan, and I'm here to argue that high-level synthesis tools should be proven correct. HLS is increasingly being relied upon for complex designs as it becomes more popular. However, HLS is known to be quite flaky, with each tool supporting different fragments of the input language and even generating incorrect designs. We argue that formally verified HLS could solve this issue by dramatically reducing the amount of trusted code and providing a formal description of the input language that is supported. We are therefore developing VeriCert, a formally verified HLS tool, which is based on ComCert, a formally verified C compiler.
Sorry, Jan, can I just interrupt there? You say
Sure.
C compiler. I mean, people shouldn't be designing hardware in C these days. I mean, all the cool kids, they're using languages like BlueSpec or Dahlia or Chisel. They're even designing their hardware directly in Coq. I mean, shouldn't you be advocating for one of those languages instead of C?
That's true, but C is actually often the starting point for these hardware designs. And once you've got a design in Chisel, BlueSpec, or Dahlia, you often want to compare that to your original C model that you designed anyways. So translating directly from C would make the testing easier. And if that tool is formally verified, then you don't even have to test the hardware that you generated.
Okay, so C may be a reasonable language then, but I mean, these HLS tools that you say that they're commonly used in industry already. Well, that must mean they're already reliable enough. I mean, to put it another way, if these HLS tools weren't already reliable, nobody would be using them.
That's true, but actually they're already widely acknowledged to be quite flaky. And we even showed that around 2.5% of just like random simple C test cases can fail in these tools. So they're only used because they make designs easier to generate.
Okay, all right. So HLS tools, maybe they're not that reliable, but still, that's not a big problem. I mean, we have existing techniques to deal with that. For instance, any design that's produced by an HLS tool can be run through a test bench, or you could use translation validation to check that the input to the HLS tool is equivalent to its output.
Well, as we showed previously, like these HLS internal test benches for these HLS tools aren't really helping that much because the tools are still unreliable. And test benches on the output of every design, you might miss quite a few edge cases that might result in weird behavior. And finally, like equivalence checkers may be computationally too expensive for really large designs. So you might not be able to, and as they have to test like the whole translation from end to end, they might even not be able to prove the equivalence in a lot of the cases, even though the designs are equivalent. So you don't get that guarantee in those cases either.
All right, so maybe there are a few bugs then in HLS generated designs, but still, I think formal verification still feels like overkill. I'm just not sure that the kind of applications that we put into HLS tools require the level of reliability that a formally verified compiler is going to give you.
Yeah, okay, I'll give you that. So it does take a lot of time to prove the tool correct up front. And like we found that it takes around like 5 times to 10 times longer to prove it correct than to actually write it. But this means that in the long run, you won't have to spend any time fixing any bugs. And it means that the only bugs that are left are features that the tool doesn't support. So in the long run, we think that the work will be basically equivalent, and you get 100% reliability out of the tool.
I mean, I don't know, Jan. I still think this whole endeavor is a fool's errand, because any HLS tool that is simple enough to be amenable to formal verification is just not going to be optimizing enough to be useful.
That's true. So like encoding algorithms is quite a lot of work. So currently our tool doesn't have any optimizations, but even then we showed that we're around the same performance as LegUp without any optimizations either. So that's a good starting point. And the more optimizations we implement, the closer we believe we can get to the full performance of a non-verified HLS tool.
Okay, so all right, so maybe formal verification is feasible there, but I mean, even then, it's not the be all and end all. I mean, it can't give you absolute guarantees about the hardware that it produces.
I'll give you that too. So in a lot of time, so a formally verified HLS tool is still allowed to fail at compile time, but this really is only has only to do with features that aren't actually supported in the tool. So it's only more engineering work that's needed to make the tool more reliable, and these edge cases are really easy to find. Then, like, because we support C, undefined behavior is also a bit annoying, but there are ways to prove that your design doesn't have undefined behavior, which then removes these edge cases that might make the hardware do whatever it wants. And finally, the only thing you really need to trust with a formally verified HLS tool is the input and output semantics of the languages. But because they're formally defined, they're much easier to read and understand, and they're not a black box like with all the other HLS tools.
All right, I think I'm convinced. Yeah, maybe HLS tools, they probably should be proven correct. All right, I'm sorry, I've interrupted far too much. I'll let you start your presentation now.
No worries, I'll just finish up the presentation. So, in conclusion, we hope that Vericert will demonstrate that a verified HLS tool is actually feasible, and hopefully, like, further research in the correctness of HLS optimizations can be helped with this formally verified HLS baseline. Thanks.